It's funny. Whenever a massive new topic drops into the education world, like, say, sustainability, the immediate reflex is almost always to just pile on more classes, right? We tell students, okay, here's another textbook, here's another lecture. But what if that's actually doing more harm than good? What if teaching sustainability as this totally isolated subject just completely overwhelms students instead of empowering them? Well, welcome to This Explainer. Today we're unpacking a really brilliant case study out of Argentina that literally flips this whole educational challenge on its head. And they did it using applied physics, industrial design, and a whole lot of concentrated sunlight. Let's get into it.
Okay, let's dive right into this. Here's a quick look at our roadmap for today. We're going to cover 1. The Educational Environmental Challenge. 2. The Fragmentation Trap. 3. The Solar Cooker Project. 4. Applied Science and Design. 5. From Design to Reality. And 6. The Power of Integration.
Section 1. The Educational Environmental Challenge, Mandating Sustainability.
So, all over the world, universities are facing this huge, growing pressure to incorporate environmentalism into their curricula. And look, this isn't just some passing trend anymore. In a lot of places, it's becoming a strict institutional mandate. It's fundamentally changing what universities are expected to teach. Take Argentina, for example. The stakes there were officially raised back in 2021 with the Integral Environmental Education Law. We're talking about Law 27621. This wasn't just a friendly suggestion from the government. This law actively promotes environmental awareness and responsibility across literally all spheres of education in the country. Combine that with the National Strategy for Sustainability in Argentine universities, and the legal and cultural expectation is crystal clear. Higher education absolutely must actively build an environmental culture. So suddenly, the big question wasn't whether to teach sustainability, but how on earth to actually do it.
And that brings us to this incredibly revealing statistic. Out of the 15 industrial design programs currently operating in Argentina, 9 of them reacted to these new environmental pressures in the exact way you'd expect. They just added specific, standalone environmental subjects to their programs. Boom, new mandate means a new class. But the Universidad Nacional de La Plata, or UNLP for short, well, they decided to take a completely different path.
Section 2. The Fragmentation Trap. The problem with piling on theory. To really understand why UNLP took a different route, we need to talk about the core pedagogical trap that universities fall into when they just add more theoretical classes. And this brilliantly illustrates that exact divide in educational philosophy. On one hand, you've got the old way. When you try to tackle a new topic by simply creating a new standalone class, you're actually increasing the fragmentation of a student's education. It's just straight-up cognitive overload. The time they have is suddenly dispersed across these disconnected subjects, leaving all that great theory totally isolated from practical application. But then, look at the other approach. We have the UNLP way. Instead of slapping on a separate environmental class, UNLP opted for a transversal approach. They decided to weave the environmental dimension directly into an existing highly hands-on practical project.
Section 3. The Solar Cooker Project, a practical intervention.
Let's look at exactly how UNLP pulled this off, because it's genuinely brilliant. So, in their second-year Industrial Design Technology course, which is a class that traditionally just focuses on teaching students how to work with metal materials and do technical documentation, the instructors introduced this totally new intervention back in 2012. Their mission for the students was super straightforward, but deeply complex at the same time: build a working solar cooker. Now think about why this is so incredibly clever. This project is essentially a pedagogical Trojan horse. The students are completely laser-focused on a hands-on, practical building task. They're cutting metal, calculating angles, trying to make a functional product. But to do it successfully, they have to deeply internalize the principles of renewable energy and sustainability. They are literally learning environmentalism by physically building it with their own hands.
Section 4. Applied Science in Design. The Geometry of Heat.
Now, obviously, building a solar cooker isn't just about sticking some shiny metal out in the sun and hoping for the best. To make this cooker actually function, these design students had to roll up their sleeves and dive into some serious, hardcore physics and geometry. The design had to be absolutely precise to capture and concentrate that solar energy. And it all comes down to understanding the parabola. Basically, a parabola is a geometric curve where any point on that curve is equidistant from a fixed point, called the focus, and a fixed straight line, known as the directrix. But let's ground this abstract math into the real-world stakes of this project. If these industrial design students get that parabolic angle wrong even by a little bit, the sun's rays are just going to scatter everywhere. There will be no concentrated focal point. No focal point means no heat. And hey, if there's no heat, nobody gets to eat the food they're trying to cook.
Now, what's really interesting here is the exact mathematical equation the UNLP students use to model their solar cookers. They use the equation y equals 180x squared. By mathematically defining the curve in this specific way, they made sure that the focus of the parabola, which is the exact spot where a cooking pot needs to sit to get hot, would be precisely 20 centimeters away from the vertex of the dish. It's just a beautiful example of where abstract theory perfectly dictates physical design.
And of course, all that geometry goes hand in hand with optics, specifically the laws of reflection. Step 1. The incident ray, the reflected ray, and the normal all have to lie in the same plane. Step 2. The angle of incidence exactly equals the angle of reflection. Because solar rays arrive at Earth perfectly parallel to one another, when they hit that mathematically precise parabolic dish, bam! Every single parallel ray of sunlight that hits the dish bounces perfectly into that exact 20-centimeter focal point. It literally takes scattered, ambient sunlight and turns it into concentrated, highly usable thermal energy. It's like a giant puzzle where all the pieces have to align perfectly.
Section 5. From Design to Reality. Executing the Prototype. Now, it's one thing to have the math and the theory drawn out on a whiteboard, right? But it's an entirely different beast to step into the workshop and physically build the thing. Let's see how this builds across a really rapid timeline. The instructors structured this execution as an intense 9-class sprint between September and November of 2012. Class 1 laid down all the heavy theory we just talked about. By Class 5, the student groups had to completely define the physical mechanisms of their cookers. Class 8 required the delivery of a comprehensive technical folder, basically documenting their entire design process. And finally, Class 9, the moment of truth, prototype testing. They actually had to take their cookers outside, point them at the sun, and see if they generated heat. To actually materialize these designs, the students had to make very specific material choices that bridge their technical learning with their environmental goals. First, they utilized 3D modeling software to perfect that parabolic curve digitally. Then, for the actual build, they used prefabricated common steel for the support structures and the orientation mechanisms, but for the parabola itself, the dish, they had to use stainless steel sheeting, capitalizing on its highly reflective properties to ensure absolute maximum solar concentration. So you see, they were learning the real-world properties of different metals by putting them to the ultimate functional test.
Section 6. The Power of Integration. Why Transversal Learning Works.
So, the big question. Did this whole educational experiment actually work? Did a metalworking class successfully teach sustainability without completely overwhelming the students? Well, the crucial point is that the outcomes were, frankly, totally transformed. The source research concluded that the old fragmented approach, just adding a new theory class, resulted in dispersed student time and noticeably lower motivation. It just kind of feels like busy work to them. But the transversal approach used by UNLP, by integrating that environmental dimension directly into a practical, hands-on challenge, it resulted in incredibly high concentration and maximum student effort. The researchers actually described it as a highly favorable synergy. The students weren't just memorizing facts about sustainability to pass a test, they were highly motivated to actually make it work with their own two hands.
Which leaves us with this final thought. Whether you are an educator, a manager, or really any professional looking to adapt to new environmental mandates, this UNLP solar cooker offers a seriously profound lesson. If you want people to actually care about sustainability, don't just hand them more theory to read. Give them a practical problem to solve. So what about you? How can you integrate sustainability into your own discipline without simply adding more fragmented tasks? Think about what your own solar cooker project might look like. Thanks so much for joining me for this explainer. I really hope this sparks some bright ideas for you today.